तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we had come up to the stress update algorithm, and we said that there are three types of stress update algorithms. One is the explicit type, another is the sub-incrementation, and the third is the implicit type. So let us now look at the explicit stress update algorithm, which will be executed in every iteration. We had seen about that in the last class. And in fact, we had seen this type of algorithm when we were doing the one-dimensional case. Remember that we had predicted using the elastic properties. In other words, there is an elastic predictor followed by a plastic corrector. The game that we are going to follow in this case is exactly going to be the same with, say, for example, starting from this point. We had called that a sigma n last time. Since it is going to be inside an iterative loop, let me call that as, say, sigma x. Okay, of course it is a vector, sigma stress vector. Strictly speaking, it's a tensor. Let's not worry about that, we know about it. So from here, what I'm going to do is to do an elastic prediction and take this point outside the yield surface to sigma e. Okay, that's the first step. Okay, so even before that, of course, you would have come to this stage after calculating u, or in other words delta u, and so you would have known at this stage what is the increment in strain. Okay, let me call that increment in strain as b into delta u. Okay, with using this, I calculate what I call as delta sigma elastic, that is the elastic predictor part of it, and that is equal to d times delta epsilon. So that's the second step. So here I check up, of course, whether I am inside the yield surface or I have gone outside the yield surface. Now, if I am still inside the yield surface, that means that my increments have taken me only from here to here, then I am not going to follow the rest of the steps. The situation is very straightforward. But if due to this incrementation, I have gone outside the yield surface, that is, in other words, I am at this point, I have to bring it back to the yield surface. Okay? So that's exactly what we did here as well. How am I going to bring it back to the yield surface? Of course, the first thing that I have to do is to find out, like I did in the one-dimensional case, where I hit the yield surface. That point, let us call it as a sigma c, where I am contacting the yield surface. Okay? So remember that we had one r and 1 minus r and so on in the one-dimensional case. Same way I have to find out what is the part of delta sigma e, or in other words delta epsilon, that I have to correct, or that I have to reserve for the elastoplastic case, and what is that part that I can add straight away with the existing stress. How do I do that? It's very simple. I know the equation for the yield surface. I had already written down that equation as f of, say, sigma comma sigma y0 is equal to 0. Of course, after the first hitting the yield surface, first time hitting the yield surface, the sigma y becomes a function of epsilon p. Sigma y becomes a function of epsilon bar p, that's equal to 0. But right now, for the time being, we are still not come to the stage, so I'm just putting that as sigma y0 only, because we are going to cross the yield surface for the first time. Now this is what I'm going to solve. How do I do that? Quite simple. I'm going to restate this as a function of, or in other words, let me remove this, sigma plus, say, alpha times delta sigma e, comma, sigma y0 should be equal to 0 in order that I calculate this contact point. So this is what will give me the contact point. That is this point here. So remember that this would result in a quadratic equation, and we will solve for alpha from this. This alpha is that 1 minus r term what you had seen in the one-dimensional case. So once I know alpha, okay, that means that alpha times of sigma delta sigma e is what I should not correct. Then I take the rest of it, 1 minus alpha term, and then multiply by delta sigma e, and that is what I have to now correct it. Absolutely right. So I will have a corresponding delta epsilon, okay, delta epsilon which goes inside the elastic part and elastoplastic part, and that is also, as we know before, 1 minus, so the corresponding things will be 1 minus alpha into delta epsilon is what I'm going to use as the elastoplastic case. How do I do that? And that is where this explicit scheme comes into picture. I have to use, of course, the flow rule or normality flow rule. Remember that the normality flow rule was written as epsilon dot p is equal to lambda dot into dou f by dou sigma. So what is dou f by dou sigma? That is lambda dot dou f by dou sigma gives you epsilon dot p, and what is dou f by dou sigma? That's the normal at the point of contact. Now there can be a confusion at this point. How am I right in taking the normal at the contact point? Okay, how am I? Because the yield surface is also going to progressively change or expand as I now calculate the stresses using the elastoplastic conditions. In other words, I will calculate the elastoplastic strains, and this will help me to expand the yield surface. So how am I correct to take that as the point where I calculate the normal? Absolutely very valid question, but since it's an explicit scheme, I start off with the calculation of normal at that point. If I have to implicitly solve it, okay, then I have to go for a Newton-Raphson iteration in solving, okay, together both epsilon bar p or delta epsilon bar p as well as the normal. So that's the difference between an implicit and that explicit scheme. An explicit scheme, in the beginning you calculate the normal and then use that normal in order to calculate further quantities. Is that clear? Okay. Now, so that is the normal that I calculate. Let me call this as dt. There are two ways of doing it. One is calculate delta epsilon p, that's here, okay, by using this relationship, so that you can write sigma trial. I'm going to write that as sigma trial, not sigma final. There's a difference between sigma trial and sigma final. Okay, sigma trial to be sigma c contact plus d times 1 minus alpha into delta epsilon minus delta epsilon p. Okay, with the contact stress I am adding whatever correction I'm going to make. Now, situation is simple. Delta epsilon p, I'm going to replace this by what? Delta epsilon p, I'm going to replace it with here. D lambda, what did I call this dou f by dou sigma in the last class? A, the flow stress. So, d lambda A. So that you will have sigma c plus d into 1 minus alpha into epsilon. Of course, both of them are tensor quantities or matrix multiplication is involved, minus d lambda dA. Is that clear? So what is this? Sigma t is equal to sigma c plus 1 minus alpha d delta epsilon minus d lambda dA. By the way, how do I calculate d lambda? Take a look at what you have done before. Tell me how you calculate d lambda. A good revision for you. In terms of d and a, I calculated d lambda. What's it? Where did we do that? We did this to calculate the tangent modulus. And what is that d lambda? Doesn't matter even if it takes a minute, go back, see where we did it. Yeah, I'm not going to say that. You just figure out what is it. I'll give you a clue. We did this during the calculation of tangent stiffness matrix. Okay, and we derived a very important relationship between lambda and epsilon p as well. D lambda is equal to delta epsilon bar p. Okay, I'm leaving it. You figure out how to do that. So I'm going to calculate sigma t using this expression. Right? Now, why is that I have said sigma t and not sigma final, sigma trial and not sigma final? Let's come back to this graph here. And what is the sigma trial? That point may be what we call a sigma trial. Okay, what essentially we are doing is to predict here and then do this correction. If you really look at this, you can split this up again into sigma c plus d into epsilon, delta epsilon. So together, which will give me sigma e minus alpha d delta epsilon minus d lambda dA. Okay, so that is, so this part is actually the correction part, this correction part. Okay, now why I have put that as sigma t is because I'm not sure when I correct it, it will lie on the yield surface. Right? Is that clear? It may not lie on the yield surface because I have not updated the yield surface and delta epsilon bar p I have not yet found out. Okay, so that is what I will do as the next step. So if I call this as the fourth step, then fifth step is a calculation of delta epsilon bar p. Once I get delta epsilon bar p, okay, I update my yield surface and get the new yield surface. Is that clear? Okay, look at this equation. That tells it all. So in fact, if you want, explicitly if you want me to write, look at this term, what this term indicates. This is d into delta epsilon, okay, d into delta epsilon, what is that term? Sigma e, okay. So if you look at this, if you want me to write that, I'll write it again, plus the first term here is delta E. What is the second term? Minus alpha into d delta epsilon. That is the sigma contact term minus sigma C. Okay, 1 minus alpha is what we are going to correct. So this term alone, that is alpha into d delta epsilon, is d into alpha delta epsilon, which we are correcting it. So this term becomes sigma E minus sigma C. Minus, of course, this term here, d lambda dA. Okay, minus d lambda dA. So in other words, this becomes sigma E minus dA into d lambda. So coming back to this point here, okay, you will see that that is the second term, that vector is the second term, okay, here, the second term here, and so the totally we come back to sigma t. Is it clear? Any questions? If you have a doubt on this, because this is a major step. Now then I calculate delta epsilon bar p, and then what do? Update the yield surface. Now since the point now which I calculate, sigma, what is it? Sigma trial does not lie on the yield surface, I do a correction. How do I correct it? Why not you think about it? How do I now correct? What is that? What is meant by correction? I have to pull that point back onto the yield surface somehow. If I do not do that, okay, then the stress will not be such that it will not lie on the yield surface. The stress will be outside the yield surface, or consistency condition will not be satisfied. So this is the major problem with the explicit scheme, that consistency condition will not be satisfied. So I have to somehow pull it back onto the yield surface. Is it clear? Why is it? Because I am updating the yield surface with respect to delta epsilon p separately. If I solve it together, there won't be this problem. Okay? So how do I do that? So I have to correct it. In other words, to give an exploded view of that, what we mean to say is, this point, this yield surface may be like this. I may go out, come back, and be at this point. That point may be the sigma trial. I have to somehow pull it back and put it onto that point, so that that point will be my sigma final. Is that clear? And that is my second term vector, d lambda dA. Okay? Now how am I going to pull back? When I pull back, it should be such that my yield criteria is completely satisfied. What I do is to have a ratio of sigma y divided by my Sij terms, 3 by 2 Sij t, okay, whole power half, okay, and then multiply my sigma t, that is equal to sigma final. Look at this equation carefully. So I use a ratio, okay, to pull this back. Now with this now new sigma f, if you calculate the yield function, okay, you will see that automatically you will satisfy the yield criteria, because this function would have done the trick. Is that clear? So this ratio, check up, it's very simple, straightforward. So this ratio is the one which is used to correct sigma t, so that the sigma final will lie on the yield surface. That means that what I mean to say is that this is now pulled back, okay, and that pulling back is what is that? Pulling back is the correction of the trial sigma t. So I have to correct it using a certain ratio such that the final sigma f will be one which is lying on the yield surface. So I do that by dividing by sigma y, whatever I have calculated now, currently, sigma y0 plus h delta epsilon p, that divided by this Sij, this ratio I multiply by sigma t, so that it lies on the yield surface.
This Sij is the deviatory part of the stress tensor of the stress tensor when it is.
So in other words, your question is, what is this Sij? Sij is the deviatoric part of the trial stress, okay, sigma t. The deviatoric part of sigma t is what I mean by Sij. Is that clear? So please do a small calculation. You will see how this would be the same as that which you will have it, which will satisfy the consistency condition. Okay, is it clear? So having done that, having now understood, let us do a small problem to completely understand every step here. So that will give us a confidence of how to solve this problem. One of the things which I want to just emphasize is that we will do the stress update at every Gauss point. At every Gauss point. Okay? So we will, right now we will do a problem. We will calculate the sigma t, sigma f, and so on. Some of you have the calculators, please keep it ready. So I will require your help to solve this problem. Let us say that we start from a point which is, say, inside the yield surface. Okay? Let me say that sigma y is equal to, say, 200 Newton per mm squared, sigma y0, okay, is 200 Newton per mm squared. For the time being, we will assume that there is no hardening factor. Okay? Let us assume that there is no hardening here. You can introduce hardening, that's not a problem. Let us assume E value to be 200,000 Newton per mm squared and nu value to be 0. Okay? We will operate with principal stresses, sigma 1, sigma 2. In other words, sigma 1, 2 terms are all 0, just for ease of doing the problems, or else it will take a lot of time to do the problem. So let us say that sigma 1, sigma 2 are 120 and minus 80 respectively. So in other words, since I said it's principal stress, obviously sigma 1, 2 is equal to 0. Right? So let me write down, for ease of doing the problem, the F in terms of principal stresses. So that can be written as sigma 1 squared plus sigma 2 squared minus sigma 1 sigma 2 whole power half. Or in other words, if I want to write the capital F, minus sigma y0 squared is equal to 0. Okay. Let us say that I have calculated delta epsilon, and let me call, and that's where I'm going to, or in other words, delta epsilon 1 and delta epsilon 2, let them be nine. Okay, both of them are 9. That is delta epsilon. So I've already done the first step. Now, if I calculate f using this, I've done that as well. From there we will start. F happens to be minus 25.64, which means that we are inside the yield surface. Okay? F is less than 0, which means that we are inside the yield surface. You don't require actually a calculator. Okay, so let us start this. So I know that I'm inside the yield surface. So what is my first step? My first step is to do, what's my first step? So where am I? Say this is sigma 1, say sigma 2, and that sigma 1, I'm somewhere.
How can we say that we are inside the yield surface?
Yes, because I have, with this stress, how can you say whether you are inside the yield surface? With this stress, I calculated f. Okay, f is, that's what I gave this as minus 25.64. That means it is less than 0. So we are inside the yield surface.
What do you mean by less than 0?
Yeah, if it is 0, if f is equal to 0, then I will be on the yield surface. If it is less than 0, we are inside the yield surface. Very obvious that, so we are here. Okay. So the first step is to do an elastic prediction. Please calculate the value of the elastic prediction sigma e. Okay, see whether we are inside the yield surface or outside the yield surface. Okay, it's not very difficult. What you have to do is, I have E here, that is the D. Okay, D becomes just 200,000 into 1001 matrix. Okay, now calculate sigma E and tell me where we are, whether we are outside or whether we are inside. So delta sigma, it's very straightforward calculation. This multiplied by this, okay, this multiplied by this, that will become, so delta sigma E, I'll write it here, will become 180, comma 180. So 180, comma 180 will be added to this, which will be 300, comma 100. So sigma E is equal to 300, comma 100. Okay, since the yield is 200, I am hitting the yield surface, so that is 200, that is 200, and that is 200. Okay, so 300, 100 is somewhere here. Okay, maybe, or even slightly less. So it is outside the yield surface. So you are going outside the yield surface. So that's sigma E. So once I know that I am outside the yield surface, now I calculate alpha. Let us see how you calculate alpha. I'll give you a minute. Just look at these equations. See how you can write down, especially this equation, and see how you can write down a quadratic form for solving of alpha. What do? So I rewrite this equation now in terms of sigma 1 plus alpha delta sigma E1, exactly. So this equation can be written as sigma 1 plus alpha delta sigma, say E1 whole squared, oh sorry, let me write it here. Okay, that's the first term, plus sigma 2 plus alpha delta sigma 2 whole squared, that's the second term, minus sigma 1 plus alpha delta sigma 1 E into sigma 2 plus alpha delta sigma 2 E whole squared minus 200 squared is equal to 0. Okay, so please expand this and tell me. So all of you can do this and tell me what would be the resulting equation. So that's the third step. We have to solve now for alpha. Look at this. Look at this equation. Expand it and write down. Quite simple. Sigma 1 squared plus, so I can write that down, sigma 1 squared plus alpha squared delta sigma 1 e squared plus 2 sigma 1 alpha delta sigma 1 e, first term. Write down the second term as well as the third terms and tell me ultimately what you will get in terms of, so you will get something like this, alpha squared into something plus alpha into something plus a constant is equal to 0. That's what you will get. Okay? Please calculate that. Rearrange the terms. You know, I hope you have written down what is delta sigma 1e. What is that? That was 120 or 180 comma 180, right? It was 180 comma 180, right? Yeah. So now write down and tell me what are the values. Substitute the values also. Yes, it will take a couple of minutes. Doesn't matter. Just do that. By the way, you know also sigma 1. Okay. So what are the terms that will come? If you have any questions, I'll answer it. So what are the terms which will come for alpha squared? Delta sigma 1 e squared will be there. You're right. Plus delta sigma 2 e squared will be there. Then sigma 1 sigma 2. So minus or plus, yeah, that's this last term here, minus, yes, delta sigma 1 into delta sigma 2. That will be the first term. Write like that for alpha and the final term as well. Then substitute for these values of delta sigma 1e and so on and tell me what would be the quadratic equation. You've forgotten delta sigma 1e 180 comma 180 and the other one sigma e is equal to 300 comma 100, right? And sigma 1, what was sigma 1? We started with 120 comma minus 80. Yes. Is it clear? Any questions? Everything is clear? Okay. What happened? Yeah. So let me give that answer. You can substitute it. You can work it out. This happens to be 32,400 alpha squared plus 7,200 alpha minus 9,400 is equal to 0. So that is the value. Yeah, it's this expansion. You can expand it, substitute the values, and I hope I'm correct. This is the value. So I'll solve for alpha, okay, alpha 1 and alpha 2. And alpha 1 happens to be 0.444, okay. Alpha 2 happens to be minus 0.667. Now, which means that that's where I cut the yield surface. Okay. So since I am moving in this direction, obviously I need to take this value, so I have to take only the positive value. Okay. And so 0.444 is the alpha 1. Is that clear? So and that is what is our current alpha. So alpha becomes 0.444. which is the value that is given on the curve? Yeah, what we are saying is that alpha 1 is this value, okay, alpha 2 is in the opposite direction, that is minus value, okay, which is in the other direction. Okay, how do I find out? Simple, substitute that, okay, into my sigma equation, find out where you cut the yield surface. So in other words, you can contact at 2 points. This is not the correct one. Okay, the positive alpha is the right one, because that's, I mean, we are finding out alpha between this and this. Okay, so that's the correct point, and so I take that point. Okay, so I take alpha is equal to 0.444. So my next step is to find out what? Delta lambda, yes, elastic. So delta lambda, and so what is delta lambda? I asked you that question. So that happens to be, delta lambda happens to be A transpose D delta epsilon divided by A transpose dA plus H. Very good. So A transpose dA plus H. Right? This is what we derived a few classes back. Okay. Now, even before I go there, I have to find out, using alpha, I have to separate out the delta epsilon into two parts, what I have to correct and what I need not correct. So tell me, what is it that I have to correct? Yes, correct, 1 minus alpha into, and what is that value? So delta epsilon, which I have to use now, happens to be 1 minus 0.444. So what's that value? It happens to be around 0.0005 comma 0.0005 comma 0.0005. That's the delta epsilon value which I have to now use. That 4, not 4, has been consumed, okay, into the elastic part. That is correct. Okay, so now we have to calculate A. What is A transpose or A? A is dou F by dou sigma. So I have to calculate dou F by dou sigma, okay, first, and this is what we are talking about as the explicit scheme. And dou F by dou sigma happens to be, okay, I can give you an explicit formula for this, and that happens to be sigma. I'll just write that down here. You know all these things. This is a standard derivation. You can derive it later. That happens to be 2 sigma 11 minus sigma 22, okay, divided by the in other words, let me write down the full equation, so then you will know it. So the full equation for epsilon dot P is equal to lambda dot divided by 2 sigma E into 2 sigma 11 minus sigma 22. Okay, in this case it happens to be sigma 1 and sigma 2, and then the second case it happens to be 2 sigma 22 minus sigma 11, and if there is a tau, of course you have one more term. Let's stop with this. So these are the two terms. So what is my dou F by dou sigma? Remember that this is equal to lambda dot dou F by dou sigma. That's dou F by dou sigma happens to be A. So A is equal to, okay, 2 sigma 1 minus sigma 2 divided by 2 sigma E, or in other words, from these two I get A to be 2 sigma 1 minus sigma 2 divided by 2 sigma E, then 2 sigma 2 minus sigma 1 divided by 2 sigma E. Okay, this is my, okay, what is this sigma E? Equivalent, which is sigma Y. Okay, equivalent stress, which is at this case happens to be 200. Okay, where it cuts the heel point at that point. So that is the A. Please calculate what A is and then substitute it. Once I calculate A, substitute it into this expression and calculate lambda delta. Here is very simple. What is 2 sigma 1? What is 2 sigma 1? Yes, this is at the point where it hits the yield surface. So what is the point at which that is sigma contact? What was that? What is that at sigma contact? Look at that. What we got when we hit the 200 comma 0. This is the values which we got. Okay, 200 comma 0. So this happens to be 2 into 200 minus 0 divided by 2 into 200. So A happens to be 1 as the first matrix, and the second one just look at that, sigma 2 is equal to 0, so minus 0.5. And what is D? D happens to be 200 0 0 0 1 0 0 1. So you know all the things here. H is equal to 0. So substitute that and find out lambda delta. So it's very straightforward, substitute these things. So lambda delta happens to be 0.0002. You can verify it. Lambda delta, it's a big multiplication, that's all. So lambda delta happens to be 0.0002. Once I calculate lambda delta, I have to substitute it into this expression to find out what is sigma t. Please do that. Let me see what you get. It's very simple. So d into a, you have to multiply d into a into d lambda. Please do that. D I have already given. Okay, lambda I have already given. Okay, a I have already given. Multiply it. Okay, and tell me what should be the correction term, this term. What should be the correction term there? And what should be the final term? Yeah, please. Is there any questions? Please do that. It's a good exercise. Please work it out and tell me what should be the term. Yes? 40 and is it okay, 40 and minus 20. Okay? Is that correct? Is everyone agrees? 40 and minus 20. And what is now the sigma t, sigma trial? Yeah, sigma e minus this. What is sigma e? Sigma e is 300, 100. So 300, 100 minus of this. So this is 300, 100 minus of this. And so what would be the value here? So obviously it is 260, 120. $260, $120, and so that is the point where we have come back after correction. And so if I plot the yield surface, okay, after going out, I have come back to that point. Okay, but unfortunately, this step of expanding the yield surface is not there because I have not given a h value. Okay, I have not given a h value. So assume that it is at the same point, right? So what I have to do now is to pull this back onto this yield surface by the correction term which I had given you. So that correction term will take this closer to the yield surface. So this in a nutshell is the complete stress update algorithm. So that's the first thing, explicit scheme. Now I said that a second scheme is a variation of this explicit scheme called sub-incrementation. What is meant by sub-incrementation? The total delta epsilon is now split into, say, 5 parts. The total delta epsilon we had is what? Not 9, right? So that is split into 5 parts. Say not 9 divided by 5. Say 5 parts. It's not that 5 exactly. It may be 10 parts. People use it even 50 parts. Okay? And then for each of these, say let's say that I'm dividing this into 9 parts. So I have not 1, okay, for every sub increment. So using this not 1, I repeat all these steps. Then again, it's in a loop now. Again, another not 1, then I go to the second step and then update it. When I do like that, because I will update my yield surface periodically, okay, many times or even most times, it would happen that the drift away from the yield surface is much less. In fact, explicit plus sub-incrementation is an excellent technique by which you can solve the stress update part. Is that clear? So this whole calculations are repeated for every sub-increment. Okay? Fine. So that's the explicit part. Maybe quickly we will run through the implicit part the next class and then take up the large deformation later. Okay, is there any questions? Stop now and we will look at, I'm not going to go to the details of implicit scheme. Again, it's a very vast topic. Just indicate how we do it. Okay, come out, proceed with the large deformation.